Hello and welcome to DataCast Solutions, Statistics and Data Mining 101 using KNIME. In this chapter, we're going to be looking at the difference between a population and a sample, the difference between them, and how to create them. Statistics is a study of data, and data is within data sets. There are going to be two distinct types of data sets, a population and a sample. And we're going to introduce a few different methods of sampling as part of this chapter. The main difference between a population and a sample has to do with how observations are assigned. With a population, you're dealing with all of the elements of a data set. That is often difficult, if not impossible, to achieve, where a sample consists of one or more observations from the population. Much easier. So let's begin by talking about the size differences. Depending on the sampling method you choose, a sample can have fewer observations than the population, the same number of observations as the population, or more observations than the population. And it is also possible to derive more than one sample from a single population. So your sample size or population choice provides what's available to you in terms of descriptive statistics. Describe the characteristics of a sample. Inferential statistics are inferences about the population based on the sample. A few other nomenclature differences have to do with a parameter versus a statistic. When you're dealing with a piece of information, a characteristic of a population, which is the entire group, such as the standard deviation, the average, minimum, maximum, that's a parameter. But a measurable characteristic of the sample is called a statistic. Some of these other differences you're going to see will also appear in the annotations to formulas, etc., that you'll see throughout the class. For example, when we're dealing with the mean of a population, it's going to be denoted by the mu symbol. But the mean of a sample is going to be denoted by x bar. And it's an important difference when you see that the formulas change slightly based on a sample versus the mean. You're also going to learn in future chapters that the formula for standard deviation, for example, of a population is slightly different than the formula for the standard deviation of a sample. So knowing the size of your whether you're dealing with a population or sample is very important to the actual execution of statistics. And you'll see, the Latin words and the symbols used in the mathematical formulas are going to change. When you're dealing with the population of a parameter, so it's going to be the symbol for the mean is going to be mu, standard deviation will be sigma, and variance is going to be sigma squared. But a statistic is going to be the mean will be x barred. And so you see how there's a change in how the formulas are being presented to you. Even though it's the same formula, it's going to be using different symbols. So there are three principal types of samples that you can create from a population: a cluster sample, a stratified sample, and a simple random sample. Let's take a look at each. In cluster sampling, it's a technique used when there is naturally homogeneous groupings that are evident inside of a population. Usually this would be done in market research, where you'd see something like this used. When the total population is divided into a set of groups, which we'd call clusters, and you'll see that demonstrated in KNIME, how we use cluster management, and then a simple random sample of the groups of the clusters that were created. A stratified sample, on the other hand, is one that's drawn from a number of separate strata of the population rather than just selecting it randomly across the whole population. For example, think of a strata as a subpopulation, an identifiable group within the population where you suspect the statistics across those various subpopulations might be different enough that you'll want to treat them differently. And finally, the most common of them is simple random sampling. What this refers to is essentially when a population of n number of objects, and a sample consists of a subset of those, lowercase n objects, and the possible samples of n objects are equally likely to occur. All that really means is that no one record is more likely to occur than another, so a simple random sampling will be representative of the population. One of the important benefits of simple random sampling is that it allows researchers to use methods that can analyze the sample results. And as an example, and we'll go through this in a later chapter, would be we can compute a confidence interval around a sample, any statistic, say the mean. And important, if I can't stress this enough, statistical analysis is not appropriate when non-random sampling methods are used. And I'm going to show you just what that means here in just a moment. Let's use a good example of what a non-random sample might look like. Assume you're a healthcare provider has doctors all around the world, and you're asked to select one doctor from each country to represent a sample data set. Do you think it would be possible to ascertain the salary, years of experience, etc. from about a population of doctors with this non-random sampling? The answer is of course not. This is not appropriate. And let me visually show you why. Take a look at this original picture here on the left. This is too much information that I want to carry. And what I represent here in the center square is a random sample. It is possible to extract less than 5% of the data from the original picture, just 5% of the pixels, and I can still carry enough information that I can see and understand what the original picture was. But in the sample to the right, I call the sample of convenience, you can see that it's possible to extract much more than 5% of the picture, retaining all sorts of data and still not gaining any useful information into the underlying picture. This is a critical difference between random sampling and what we refer to as a sample of convenience, where you just take the data that's available to you. The data captured in a convenience sample, what I'm hoping you're drawing here, it's not just less rigorous data. I have been in more meetings where people have said, well, it's more like a silver standard. Sure, we'd love to have the gold standard, but we can't, so let's take the data that's available. A sample of convenience is not just less rigorous or less quality data, it's bad data. If you're going to be making business decisions, it needs to be based on good data. In statistics, we use something we call the confidence interval to express a degree of uncertainty we have associated with any statistic related to a sample. It's an interval estimate combined with a probability statement. So, say for example we're taking a survey of who you're going to vote for president. We would describe the confidence level to describe the uncertainty associated with the average. What percentage of people are going to vote for candidate 1 versus candidate 2? We might describe that interval estimate as 95% confidence interval. And what we mean by that is if we took repeated samples over and over and over again, we would expect the true population mean to fall within the sample means 95% of the time. Let's assume that I want to create a random set of 2 balls from a population of 3 balls. I could, of course, do this many different ways to obtain a random sample. But in this case, let's look at it and say I've got a funnel here, and I'm going to pull the first 2 balls out. Each of the n population members is assigned a unique number. The numbers are placed in a bowl and thoroughly mixed. Then a blindfolded researcher reaches in and selects 2 numbers. All possible samples of a particular size are equally likely to occur. So you could get 1, 2, 1, 3, or 2, 3. Those are the only choices, and each one of them is just as likely to occur as the other. Now, one last thought about sampling when you're doing random sampling is replacement. Suppose we're using the method that I described above, and we say after we pick a number, we have to decide, do we put that number aside or do we put it back in the bowl so that we can draw that number back again? That's the difference. When a population element can be selected more than one time, that's referred to as sampling with replacement. When a population element can only be selected once, meaning you don't put it back in the bowl, that's sampling without replacement. Of course, that method is not going to be done here anymore. Today, we use computers to perform tasks like this, and a product like KNIME has all the built-in capability to create samples for you automatically. So before we look at the demonstration, let me just first point out what I hope is obvious, but this class is going to be focusing on teaching you statistics and implementing those statistics using KNIME. This is not meant to be a class to teach you the introduction to KNIME. So my understanding coming into this is that you already know how to use the database readers and CVS readers and file readers and so on, and you know how to connect nodes. And if not, Datacast has classes available to teach introductions to KNIME so that it'll get you building your first workflows. So that knowledge is a prerequisite to taking this class. So let's take a look at KNIME now and see how we would implement some of these sampling techniques. So to start with, I've got a database reader node here. And if I show you the data from the reader node, you can see that I've read a population. I've got 16,044 records in here, more than I want to use in my processing. So what I'm going to do here is, down here in the node repository, I've got a few different sampling techniques. So let me start with the first one. Let's put the row sampler out here. Now, what this does is executes sampling without replacement. So if I draw randomly, that's without replacement. So it's going to simply put records out. I can choose an absolute number that I want or a relative. I want 10% of the file versus I want 100 records. You can force it to take it from the top. You can do a stratified sampling by providing it the name of the field that would use to draw the strata. So again, the subpopulation, if you will. And if your test needs to be repeatable over and over again, you can, of course, use a random seed, which will force the row sampling to produce the same output over and over and over again. So in this case, I'm going to go ahead and say I want random sampling of 10% of my data. And when I execute it, and I look at my sample data, I've got 1,604 records. Okay? So that's without replacement. Now, Bootstrap sampling is a different technique. Basically, it's with replacement. So with the Bootstrap data set instead, again, I'm going to specify this in terms of a percent. So I'm going to say 10%, and I can choose an absolute size, and I can use the random seed. But again, notice here up in the right corner here, it's telling you this draws rows from the input with replacement, which means it's going to contain duplicate rows while other rows are not going to be present in the output at all. So if necessary, basically it's going to generate an original row ID if you want to generate that, and then you can specify a specifier to generate the new row ID for the divider. So let me go ahead and execute this. And you see I've got two samples here, the Bootstrap samples, which represent the 1604, and you'll see how it's updated the row ID to represent each one of these samples. And I can also see the holdout samples, the rows that didn't go into any of the sampling. This technique is often really good when it comes to creating data models, so we'll be talking about that later. And then finally, equal size sampling. In this technique, I'm going to remove rows from the input data set so that some categorical column are equally distributed. So in other words, if I was going to say, I've only got one category or two categorical titles here, but maybe I might have store ID or something like that to say I want 100 records from each store. So I could use this to create a count and say I want to create exact records or exact titles. So my sample is now based on title of the movie. So I wind up with many more records than the 1,604. All right. That concludes the demonstration for how to do sampling in KNIME. So a quick chapter summary. Population includes all the elements of a data set. A sample includes a subset of that population. A parameter is a characteristic of the population. A statistic is a characteristic of the sample. The subset of a population in which each member of the population has an equal probability, that's a random sample. It has to be unbiased representative group. And the replacement option, when a population element can be selected more than one time, we're sampling with replacement. If it can only be selected one time, we're sampling without replacement. That completes this chapter of the class. Feel free to move on to the next chapter.